Good afternoon, everybody. It's Thursday, September 14th, 2023. It's the fourth lecture, and we are looking at examples of dynamical systems who are strongly contracting. And they're not only figuring out their contracting, calculating the rate, trying to understand how optimal it is, and also looking at the method of proof for it. We looked at the linear matrix inequality proof based on the Schur complements that allowed us to get an estimate for the primal dual contractivity rate. There are many cases where one can use LMIs. In fact, there's a lot of literature on it. In fact, the majority of control theory is based upon quadratic Lyapunov functions. But I would like to convince you that sometimes the infinity norms are also useful. Remember, yesterday I described for you the motivation for non-Euclidean norms, including the work by Polyak. So now, allow me to complete the treatment of the neural network with respect to which is contracting, well, finding sufficient conditions for the neural network to be contracting with respect to non-Euclidean norms such as the infinity norm. And I stated the result. The result was that if the synaptic matrix has a log norm which is less than 1, then the system is contracting with the given rate. And before I proceed, allow me to look at the condition. What does it mean that the log norm is less than 1? It means that Wii plus the summation of the absolute value Wij is less than 1. So one of the beauty of this condition is that it has a very clear graph theoretical interpretation. It means that the sum of the incoming edges into node I, so all of the edges of the, or outgoing, depending upon the direction the convention you have. So Ij is the signal that travels from node J to node I, and it gets integrated at node I. The sum of the strengths of those synaptic connections in an electric circuit sense, it is a charge that is traveling from J to I. The sum of those weights, Wij, the sum of those weights needs to be upper bounded by 1. And or possibly you may have some dissipation. Wii could be negative, which is helping to render that particular neuron more stable, more dissipative, right? So it's a condition on the total synaptic strength into a given node. So it's a nice interpretation. So let's do this proof because it's very simple and it's very elegant, and it's very different from the. Oh my goodness, it's very different from the. Wow. Okay. It's very different from the LMI brief. So. How do we do this? Well, I've already started it earlier. Compute the Lipschitz constant of the vector field. Okay, so let's just use the definitions one after the other. It is, and let's use the differential version, which is to say the supremum of the log norm of the Jacobian. It's exactly the definition, no more, no less. So the supremum of the log norm of the Jacobian. Now notice that there is a control signal U. And now I'm anticipating something that we'll be discussing later. Sometimes you have a dynamical system in which an exogenous parameter appears, like a control signal, a disturbance or something. So maybe you want to establish contractivity for all values of the exogenous signal. So here I did supremum over all x's and u's, not just x. All right, fine. I calculate, the main thing is that I calculated the Jacobian, right? Okay, fine. So now I've already mentioned that the log norm has this translation property, and the translation property implies that this identity matrix can be just brought outside and it becomes -1. And then I have the supremum over all x's and y's of the log norm of, well, let's read this carefully. Actually, let's read this carefully. So what is going on here? Because this looks confusing. I got the Jacobian of phi evaluated at this quantity. I do have one too many parentheses. Oh, that's terrible. That's okay. I'm going to quickly fix that for you. There we are. This looks better now. Let me try it again. I have the Jacobian of the activation function evaluated at Wx plus Bu. And then I need to take the Jacobian of the argument of the activation function with respect to x. Wx plus Bu, Jacobian with respect to x, is just W, right? So inside the parentheses, I have the product between d phi and W. Now, d phi is a diagonal matrix, right? Because we reviewed that before the break, and we saw that it's a diagonal matrix because it's a diagonal nonlinearity to begin with. It is the output of the single neuron that gets run through the activation function. It's not a global function that takes all the arguments. So now, if you look at this supremum here, you are allowing relatively arbitrary values of the argument Wx plus Bu. These are going to be completely arbitrary. I have a diagonal matrix, which then multiplies W. And now I'll make the case that we were assuming that the activation functions take the derivative of the activation functions takes value between 0 and 1. Between 0 and 1. No matter what the argument is, you're never outside of that range. So you know what? Let me rewrite this problem, this supremum over x and y, which looks so hard to read. Let me write it in a way that is rather easier. I will a little bit change notation. I will imagine that each entry on the diagonal of the derivative of the activation function is just a scalar number d. I have n such derivatives. So, and they all take value in 0 to n. So now I write less than or equal to here. Why? Because even though x and u are arbitrary, I know nothing about w and b. For example, w and b could be equal to 0. If they're both equal to 0, the argument here is always 0. But if the argument is 0, perhaps d phi does not take any arbitrary value between 0 and 1. If you are maximizing a function over a domain, what is the language I'm trying to use? I am not sure that the argument takes all possible values between 1 and 0. And I am not sure that the derivative of the activation function will take all values between 0 and 1. So I'm just allowing this to be a larger domain. And so the right inequality here is to just say upper bound, because here I'm allowing lowercase d to take a value over an even larger set than I am sure it will take. Okay. So now this is interesting. What do we have here? We have the maximum with respect to d. D takes value in a compact convex set. I have a nice compact, it's a hypercube, as simple as it gets. And I am maximizing a function log norm infinity of the diagonal of d times w. Yesterday, I told you that the log norm is a convex function. So you are maximizing a convex function. The maximum of a convex function will always appear on the boundary of the set. It cannot be in the interior because it's a convex function. Moreover, this particular set is a polytope in high dimension because d takes value between 0 and 1. So the set of matrices of the form diagonal d times w is a polytope of matrices. How many vertices does that polytope have? Well, d1 is either 0 or 1, 0, 1, 0, 1. So it's 2 to the n. There are 2 to the n vertices to the hypercube 0, 1 to the n. And therefore, there are also 2 to the n vertices of the polytope of matrices diag d times w. I need to maximize over this polytope, which means that the maximum is going to have to be one of those 2 to the n vertices. So at first, you may feel discouraged and say, oh my goodness, I have a combinatorially large number of vertices that I need to check. Okay. However, this problem has enough structure that, in fact, you only need to check only 2 of those 2 to the n vertices. And let me tell you what they are. They are the vertices where d is equal to 0, the vector of 0, or d is equal to the vectors of 1, all ones. This is a claim, which I will prove in the next slide. Allow me for a second to finish the proof, assuming that the statement is true, that the claim is true. Well, then, instead of maximizing over 2 to the n vertices, I'm going to maximize over just 0 and the vector of ones, which is w. 0 times w is 0, 1 times w is w. Now, the log norm, infinity log norm of the matrix equal to 0 is 0. And so here I have the maximum between the number 0 and the number log norm infinity of w, which is exactly the definition of the positive part of log norm of w. So this is the proof. This is the final statement that I wanted to get to, right? Okay, so what is left unproved? I need to check that this particular step was correct, that really I only have 2 vertices instead of n, instead of 2 to the n that I need to worry about. So this seems like it's difficult, but it's actually elementary. So I'm about to do some elementary calculations for you. And the key idea in here is that, okay, I'll come to that in a second, but it's a very simple key idea. So let me just set up some notation to simplify the proof. So I'm going to define, remember, the log norm of a matrix is computed as the maximum row sum, where the row sum is not of the entries. I need to take the absolute value of the orthogonal entries. I have said it so many times that I'm bored of repeating it, okay? For a second, allow me to define a symbol for this particular row sum. Let's use this bold lowercase r sub I of the matrix A. Is the ith row sum of the matrix A, where I take absolute values of the terms of the diagonal. If I have to say one more time, I'm going to kill myself. So now, first simple observation, that when you consider the matrix DA, and by the way, my apologies, I guess I should let, this slide is intended to use the matrix W, but I wrote it with A. Forgive me, I didn't make, just a little typo. So if I left multiply the synaptic matrix by the vector of D, and I look at the ith row of that matrix, you know what it is? It's the old row multiplied by the scalar DI, by the ith entry of the diagonal matrix D. So what happens is that the key idea is that this absolute row sum of the ith row of DI is just a little scalar DI that multiplies the absolute row sum of the matrix A, because everything is being multiplied by DI, and DI is between 0 and 1. It's non-negative. So whether you take absolute value or not, it doesn't matter. It's non-negative. You can bring it outside of the absolute value if there's an absolute value, or you leave it. Okay, perfect. So now I'm ready. To do I have all the notation and everything. So, okay, this is the ugly looking optimization problem from the previous slide. Look at the worst case value over the hypercube of this particular polyhedra of the log norm of this particular polyhedra of matrices. Now, let's, by definition, plug in the formula. It's still the max, so that is not changed. And then I put in log norm infinity of dA, and because I calculated that the log norm infinity is the worst case absolute row sum left multiplied by di. And right now I'm just dropping, you know, this ri, it's ri of a, not of the a, right? It's just for a. It's just a number. Now, what happens is that I'm maximizing n functions, but the functions are decoupled. They're just n decoupled functions, so I can just maximize each one of them. It is the same. And the ith function depends only upon di, not upon dj. So what happens is that you can change the order of the two max operations. You have maximum with respect to I, of the maximum only with respect to di, because dj's do not appear, of this quantity di ri. Oh, now the problem is much easier. And you know why? Because now I am maximizing a function of di, but it is a linear function of di. I mean, that's just a very simple problem. I am maximizing a linear function, and di is on a range. So the maximum of linear function is going to be, if the linear function grows, it's on the right. And if the linear function decreases, it's on the, if the function goes like this, it's on the right. If the function is like that, the maximum is on the left. That's all there is. It's just a linear function. It's either, it could be that ri is 0, in which case it doesn't matter what di is, but if di is positive, sorry, if ri is positive, then you want to maximize it. So you select di equal to +1. And if ri is negative, then you select di equal to 0, right? That's all there is to it. So If Ri is positive, the maximum is achieved at Ti equal to +1, and the value is Ri. If Ri is negative, the maximum is achieved at Di equal to 0, and you get 0. Does that make sense? That's because necessarily Di is between 0 and 1. I'm still left with the maximization with respect to I outside of the curly brackets, right? So now I have the maximum of this and that, depending upon some clause. I'm going to drop the clause, and that maximum is upper bounded. If I just say the maximum of this and that, logically I have enlarged the possible values, and so it's an upper bound. So I'm dropping the if clause. Let me repeat it again. You are looking at the maximum of two functions. You apply function 1 when something happens, function 2 when the opposite of something happens. You know what? This is upper bounded by the maximum of two functions, because I don't worry about the FOS. And the maximum is two functions, the maximum of these quantities, the maximum of Ri, comma 0. But the maximum of Ri is the infinity norm of A, the infinity log norm of A, and the maximum of 0, well, it doesn't even depend, it's just 0. And this is what I had claimed earlier, right? I had claimed that this 2 to the n vertices were really just the values of the two corners. There's also another picture that I could draw. Let me cement myself in drawing a picture. So the hypercube, right, where this is the point 0, 0, 0. This is the point 1, 1, 1. So your function achieves its maximum at either one of all these vertices, but we now know it's necessarily either the 1, 1, 1 or the 0, 0, 0. Just to give you a bit of an idea. So that's the end of the proof, right? I have finished my proof of contractivity, of sufficient conditions for contractivity for my neural network. And I did not have to, this one is not where you have to make a conjecture, what is the P matrix, you have to make a manipulations, magic simplifications, try to guess. Here, this is much simpler. I also did not optimize the weight. There are no weights here. It's just the infinity norm. We can optimize with respect to diagonal weights, and it does get a little bit more complicated. It's a little bit of a longer story, which I would like to skip. I'm not sure it's well worth it of the time right now. Any questions on this proof of example number 6? It depends upon you. No, it's not 0. No. So if U is 0, even then it's not clear. I by chance happen to have plotted the two activation functions that cluster with 0. But I didn't ask for that assumption. I only asked for the assumption that the derivative is between 0 and 1. So no, the equilibrium is not 0. Yeah, it does not need to be 0. Yeah. There could be a bias term. The bias would not play any role. No. All right. Okay, so this is an example. Later on, we'll talk about how do I use this information about the infinity log norm contractivity for some useful tasks. Let me keep doing my examples. In the remaining time, I'm going to do more examples, and then I will do a review for you the theoretical properties of contracting systems, which is the following section in the slide deck. So you may ask me, Francesco, okay, you gave me a sufficient condition, this graph theoretical interpretation for the contractivity with respect to the infinity norm. Can you use other norms? Now, recurrent neural networks are very, very important, as you know. There have been millions of papers. Millions is too strong a word, but tens of thousands of papers, and it's really extremely interesting. So, and there will be reasons why it is interesting to try to use also the Euclidean norm. And what you're seeing here is a result that has to do with the 2 norm. It is a weighted 2 norm. So here I have various cases. In all cases, it's a weighted 2 norm, right? You see here. So this is a weighted 2 norm sets of results. And these are obtained under the assumption that the synaptic matrix is symmetric. So I do not know how to get good non-conservative results for the 2 norm contractivity for the asymmetric case. But there are easy upper bounds, but they are very conservative. This parameter here, I'm basically I have a synaptic matrix. It's symmetric, so it has a bunch of eigenvalues. I look at what matters the most is the largest eigenvalue, which is also the spectral abscissa of the synaptic matrix. The largest eigenvalue, they're all real, right? And so this, I'm going to abbreviate it with lambda sub w, just for simplicity. And the results are when you have a synaptic matrix which is symmetric and has a negative largest eigenvalue, which means negative definite. And then when it is negative semi-definite, and when it has positive eigenvalues between 0 and 1. And then I'm not writing down the results, but when the eigenvalues of W are larger than 1, when the dominant spectral abscissa, then the system is not contracting anymore. But if you were interested to, I could compute the one-sided Lipschitz constant for it, and it would be an expansive system. So I have a formula for that, but I'm not going to worry about it. And here I have the specific rates. In the best cases, just like before, the best rate is 1, and then it decreases. It becomes smaller and smaller as I let my synaptic matrix move towards the point of lack of contractivity, right? I am not going to spend time telling you exactly what are the weights, okay? In the weighted 2 norm. Nor am I going to write down the proof. The proof is well, okay. Here, the first row of my purple proof here is a definition of what the weight is, and it's a very weird and unusual weight matrix. Okay, so the construction is very surprising, and what is not surprising by now, given what we have done during the last hour, is that the proof is an LMI-based proof, and I have limited intuition for it. I know it is true because I perform my LMI acrobatics, and at the end, I hold on to the the other acrobats, and the proof is complete. But precisely the intuition for the proof, I do not have. It's again using various properties of linear matrix inequality for positive definite matrices. And in particular, also there is this Sylvester's law of inertia, which helps you manipulate these matrices. Now, one last thing I will say about these 2 statements that I have given to you about contractivity of neural networks. When the synaptic matrix is symmetric, this analysis applies, and the estimates that you get are sharp. You cannot get contraction rates which are better than the ones that are stated here. So in a way, this is the optimal analysis for the symmetric case. Whereas in example 6, I did the non-Euclidean analysis, which is simpler and cleaner and elegant. This works in every case. I can do a little bit of optimization on it. I can, which I didn't do, I can add a weight, a diagonal weight. I can improve the contractivity rate. But it is not clear to me that if I found a better norm, I would be unable to get a better rate. So in other words, this may not be the best possible rate at all that one can get. Okay. Any questions on neural networks? Right now, I'm not using them for anything, but I'm going to study properties of contracting systems, and then we will use a little bit on the neural network later on. So the last example that I want to do at this point in time is I want to talk to you about a very classic model in control theory, which are nonlinear dynamical systems in Lur'e form. These systems are described by a triplet ABC of matrices that you would have encountered in your studies of linear systems. So x dot equal to ax plus bu, and then y is equal to cx. So that's your standard linear system. And then you take the output and you run it through a nonlinearity, and then you feed that back into the system. So this is a simple block diagram, as you might be from here. And you ask yourself the question, when is it true that my nonlinear system in Lur'e form? Well, classically, the question is the system stable? But of course, in the context of this lecture, the question is the system contracting? Well, and you're going to have to make assumptions on ABC, and you're going to make assumptions on the nonlinearity, right? Because otherwise, I don't have enough data. All right, perfect. So I am going to consider the single input, single output case for simplicity of exposition today. And I'll give you references where the multi-input, multi-output case is studied in the next slide. So because it's single input, single output, the nonlinearity is just a scalar function. Otherwise, it would have to be again a nonlinear diagonal, similar to the activation function, right? Correct. And typically, I'm going to work with this assumption. I'm going to work with the assumption that my activation function is differentiable. Again, really sufficient to argue it's locally Lipschitz, and which means it's differentiable almost everywhere. And these bounds hold almost everywhere. I can write the bound in an integral way, so I don't have to even write the derivative. But it's easier to write them as function of the derivatives because you get that immediately. And it's so the derivative of the Lur'e nonlinearity is upper and lower bounded by two parameters. Let us call them sigma 1, sigma 2. And graphically, you have these bow ties. What does this mean? At every point, y, it's a scalar variable, you must be inside this kind of a bow tie, because the derivative cannot be smaller or larger than something. So you at this every point the function is captured inside these regions. This is corresponding to the largest derivative, and that's corresponding to the lowest derivative. Yeah? Okay, fine. Now, okay. So I am going to characterize is a better word, because I do not lose any information. So I am going to another way to say it is translate my slope constraint, phi prime is between sigma 1 and sigma 2. I will translate it into an inequality of this form, in this particular inequality here. Okay, I will define a matrix M symmetric. I will call it an incremental multiplier matrix for the nonlinearity psi, determined by psi, and that characterizes psi. And basically, I am saying, if you give me an arbitrary Lur'e nonlinearity psi, a matrix M symmetric is an incremental multiplier matrix of psi. Whenever the following happens, what happens is that if I left and right multiply M by the same vector, the vector contains y1 minus y2, c of y1 minus c of y2. This contraction, it's a quadratic form defined by the matrix M, is always non-negative for all y1 and y2 in the reals. Does this make sense? So if you give me nonlinearity, the matrix M is a valid matrix. It's an incremental matrix multiplier if this quantity is always non-negative, no matter how you select y1 and y2. Does that make sense? You give me a matrix M, I check it. If it's always non-negative, okay, it's an incremental multiplier matrix. Specifically, for a slope constraint psi1 between sigma 1 and sigma 2, psi prime, the incremental multiplier matrix that works out well is this particular one. Now, we're looking at expression. M, of course, it is going to depend upon sigma 1 and sigma 2. And it has, I think that you can read it. I don't need to repeat it. Minus sigma 1, sigma 2. It's symmetric, sigma 1 plus sigma 2 over 2 on the 1, 1, on the 1, 2, and 2, 1 engine. All right. So this entire thing in parentheses in the second half of the slide is a bit arbitrary. Why are you doing that? Well, right now I have gone from a description which was just a inequality between derivatives to something that begins to look like a linear matrix inequality. This is saying that no matter how you select y1, y2, that contraction is non-negative. I contract the two vectors into the matrix, it's non-negative. All right. So let me make the statement right now. I'm just going to make the statement and maybe we'll do the proof. The statement is as follows. Consider your Lur'e nonlinear dynamical system, right? Perfect. Assume that the nonlinearity is described by an incremental multiplier matrix M. And then, if something exists, then my Lur'e dynamical system is strongly infinitesimally contracting with the rate C with respect to a weighted 2 norm. Okay, so what is this something that must exist? Well, it is the positive definite weight P and a positive scalar C. And all together, all the quantities that I have introduced, so the triplets A, B, C, and the activation, the nonlinear, the Lur'e nonlinearity described by the multiplier matrix M, and now the matrix P that I'm looking for, and the contraction rate C that I'm looking for. My laptop is dying. Altogether, the three of them are supposed to satisfy this particular LMI. Does that make sense? This LMI looks complicated. This is a block LMI, right? If you look carefully, these are 2 by 2 blocks, right? And here, this is a block matrix times a block matrix times a block matrix. We should check the dimensions. I would encourage you to check the dimensions, and you will see that it will check out. Everything works out here. So, and so basically, you now have the following problem. I give you A, B, C, and M. A, B, C, and M. If I, sorry, A, B, capital C, capital A, capital B, capital C, and then M, I am left with C and P. C and P are multiplied together. So it is not true this is convex jointly in C and P. But what it is true is that if you fix C, then searching for P is searching for a feasibility LMI problem. So that's a computationally tractable problem up to mid-sized dimensions in the thousands. It's hard to go in the millions, but you can go to thousands. It's not a linear program which you can push into the millions and even higher. But you can solve LMIs of in the thousands, I am told. If you give me a performance level C and you find the P, now you can make C larger and see if you can still find it. Huh? And so now maybe let's say you can still find it. Okay, increase C again. And now if you cannot, then you do bisection to find the largest possible value of C. So does that make sense? Yes. So now this is a relatively standard approach to robust stability analysis. This is for contractivity. Based upon defining and then running LMIs of, this is actually a small LMI, only 2 by 2 blocks, but people look at even larger problems. And I also want to clarify, this condition here is nowhere near as explicit and interpretable and actionable as the ones I have shown to you for is my function strongly convex, or is my synaptic matrix the sum of the incoming synapses less than 1. Right? Those were very explicit, very clear, right? Here now, instead, this is very computational. This is like you give me a nonlinearities, I characterize them through incremental matrix multipliers, and then I go to Python and I just run the code until I see if I find it. Okay? So you cannot understand systems with parameters here, because now it's all very numeric. How does the proof of this theorem work? It's again an LMI-based proof, the third proof that we mentioned today. You have to, basically what you are going to prove is that this LMI here, you find the P and you see inside this LMI, plus the definition of the incremental multiplier matrix M, the one that tells you that y1, y2 multiplied into M, is always the one in the previous page. Together, those two LMI imply the contractivity LMI that we've been talking about all along. That's the heart of the matter. And specifically, the one tool that I have not described in great detail is called the S lemma. So Jakubowicz in the 60s and 70s introduced the S lemma, and it has to do with when is it true that if one LMI holds, then another LMI holds, and there are conditions for that. If you want, I can go over the proof. It's actually not very. It's in the book. You can look at the book. It's actually really simple. It's simpler than the one we saw, and not the hardest that I did not look at I don't know if it's harder. It's just that it's really counterintuitive. The one for the symmetric synapses, it's really counterintuitive. I mean, it's really arbitrary. The one that we've seen at the beginning of this morning's lecture for the contractivity of the primal dual gradient, it was step 1, step 2, step 3. There were a lot of moving parts, but at the end of the day, perhaps it wasn't all that complicated. Just a little bit of magic in the choices of the parameters. This one here now for the Lur'e case, it's relatively straightforward. It's literally 3-4 steps, and it works out. Okay. I have finished my question. Yeah, these conditions end up looking similar for this particular type of nonlinearities. I and others have not yet been able to build rigorous bridges between these fields. If you go back to what is the condition for contractivity and what is the condition for dissipativity, one is the condition on a vector field, the other one is a condition of an input-output system, and there has not been a satisfactory rapprochement between these two theories. But there's a lot of interest in that. Lots of people have mentioned it, discussed it. I think there are little results. I am unable to present them to you, but not quite general a theory as one would like to have. Yes, yeah, you can. Yes, this is you can show that this is equivalent to a certain infinity gain being less than 1 and so on and so forth. Yeah, I apologize. I'm not ready to go into that detail right now. All right. I think I have about an hour. I've done my first group of examples. There are other examples that I want to do later, but now it may be time for me to just mention some properties. Okay, some of them are going to be one slide, and others are going to be a little more complicated. So let me spend the next. Let me get started, and we'll see how many of these I can cover today, and then hopefully tomorrow I can do the example applications. So the first property of strongly contracting dynamical systems is one that should not be surprising because we've already proved it. That is to say that, okay, so I take a time invariant vector field and I assume it is strongly contracting with respect to a norm, and I let C be the contraction rate. Then at each time, for any positive duration t, the flow from time 0 to time t, so for duration t, is a contraction, is a discrete time contraction. By the way, with factor e to the minus ct, which is to say that the solutions come together, right? The distance between solution decreases exponentially time. So that is, we already proved this when I did the continuous time Banach contraction theorem. That's exactly what we proved. I just put it here to remind ourselves. The new result is that, well, okay, we knew there was an unique equilibrium, unique, globally exponentially stable. The new result is here. V1 and V2 are the global Lyapunov functions. So what are V1 and what are V2? V1 is just the distance between your current position and the fixed point, the equilibrium. And we already knew this because this is the proof that we did in the Banach contraction. The one that is surprising, or it is new, is V2. So I would call that the speed of the vector field. So the norm of the vector field is itself a Lyapunov function. By the way, I put squares here, and they're really not quite needed. A Lyapunov function and its square or its square root are they have special certain property, and they're also now. By the way, what is a global Lyapunov function? Because here I use a very specific language from Lyapunov stability theory. You need to satisfy various properties, and I don't want to go into too many details right now because but they're all satisfied. So it's globally positive definite, the derivative is globally negative definite, and the function is radially unbounded. These functions here, the first one is obviously radially unbounded because the norm is radially unbounded because it's homogeneous. And it turns out that you can show that even the second function, the the norm of f is radially unbounded. You can show that from the contractivity property. All right. The third observation is really just a throwback to the gradient example. The third observation says that if the Jacobian of f is symmetric, then for those of you who have studied differential geometry and the Poincare lemma, you would know that if the Jacobian of a vector field is symmetric, well, then the vector field is integrable and there exists a function. And this function can be, for example, computed by means of this integral here that I'm highlighting. But the bottom line is that you really proved again that V3 is strongly convex and F is minus the gradient of V3. Does that make sense? All right. Well, if your vector field is the gradient of a function, there is even a third Lyapunov function, not only two. And the Lyapunov function is okay. The function whose derivative you are. Does that make sense? Here's a little exercise. You consider a very simple function, like a quadratic function. V3 equal to 1/2 x transpose qx. You can check that V1, V2, and V3 are different. They're three distinct global Lyapunov functions. They're not the same. I would like to just do the proof briefly because it highlights again the power of the tools that we have seen yesterday. Okay, this was the old proof that we have already done. So if you do remember, this is the curve norm derivative, you immediately get via the Gronwall lemma that the distance decreases exponentially fast. Now, consider V2, which is the speed of the vector field, or the square of the speed. So now, let me just make a comment. If you compute the time derivative of the vector field evaluated, I mean to say entry-wise, right? What do you get? You get the Jacobian of f times x dot. But then x dot is equal to the Jacobian of f times f, right? Okay, let's remember that. Now, I wish to calculate not the derivative of f, I wish to calculate the time derivative of the norm of f. And how do I do that? Well, I'm going to use again the curve norm derivative formula, which is to say I left multiply by one more copy of the norm. And on the right-hand side, I get the pairing between the derivative of f and f. But the derivative of f is nothing more than Jacobian of f times f into f. But now you have the pairing between a matrix A, V into V. And now you can use that property, which I told you is called the Lur'e identity for arbitrary norms. Otherwise, it would be the standard Courant-Fisher theorem for the two norm, which tells you that you just pull out the log norm of the matrix, and you're left with the inner product or the pairing between the two vectors, which are the same, right? Now I have the log norm of the Jacobian, and I'm going to upper bound it by its supremum value, which just so happens to be the one-sided Lipschitz constant of f by definition of one-sided Lipschitz constant, right? And the remainder is f into f, which, as you remember, f into f, if you go back and you look at the axioms of the pairing, it's the norm of f squared. And this is the end of the proof, because now I have proved again that the derivative of the norm into the norm is upper bounded by minus c, the norm squared. So I can eliminate the two with this. I eliminate them, and I found out that the derivative of the norm is exponentially decaying with rate minus c. And I use the curve norm derivative formula and the Lur'e identity, just like before. If you want to read more about the Poincare lemma in the context of contractivity, this is a recent paper that writes down this detail of the proof of the V3 function. All right. So the first property that I wanted to tell you is now in my theorem: unique global exponentially stable point, trajectories come together, 2 or 3 Lyapunov functions, the distance to the equilibrium, and the speed. So your vector field is, what this is saying is that the speed of the vector field, the velocity at which you move is decreasing exponentially fast with rate c. So if you have a trajectory and it's moving, it's slowing down. Not only you're going to a point, but you're slowing down exponentially fast. In some problems, it works like this, that your system is contracting in a region, it's locally contracting. You enter the region where you're locally contracting, and now you slow down. And now you can write conditions that say, because you're slowing down exponentially fast, perhaps you are able to slow down and stop before you leave the set. If you stop, you have an equilibrium point. And if instead you slow down, but not enough, and now you leave the region where the one-sided Lipschitz constant is negative, where you are contracting, well, unfortunately, after that, I don't know anymore what happens. Okay. All right. Second property. This is so cute. It goes like this. Again, we can contract things. No, we can arbitrary norm, and we can differentiable map vector field F. Now, you all know that if I have x dot equal to f of x, and I wish to integrate it over time, let's say that at the given time I'm at the given value, let's call this xk, then I evaluate f at xk, right? And then I take a little step forward to xk plus 1, and there is a step size, right? And I go here, right? And this is called forward Euler integration. It's an approximate numerical method to compute an approximate solution of the differential equation on a computer. All right. So my question is, when is it true? Well, actually, let me just tell you the answer. It turns out that, okay, so this is the one step of the forward Euler integration algorithm. Now, this one step of the forward Euler integration algorithm, this is now a discrete map, right? Because this map means, xk plus 1 is equal to the identity map plus alpha f applied to xk. That's not the identity matrix, it's the identity map. All right, fine. So is it true? When is it true that the identity map plus alpha f is a contraction in discrete time, right? It's a reasonable question. Because maybe I actually wish to compute that equilibrium. I know the equilibrium exists. I know it's unique. I know that the solution of the ODE converges to the equilibrium. But what if I wanted to compute it? You know, I need to use a numerical integration algorithm. Okay, well, is the numerical integration algorithm a contraction? That's a very reasonable question. Not only that, but also, not only I want to know if it's a contraction, maybe I want to also choose the optimal step size so that I have, fast convergence, right? Okay, so the point is this. I have the good news, the happiness, the happy role of sharing with you that these statements are equivalent. The dynamical system is strongly infinitesimally contracting, and there exists an alpha, a step size, such that the Euler discretization is a discrete time contraction. And there's a ton more detail that I could add here. In fact, I'm going to add it in a second, and it's going to get scary. But for now, I'm just making the case that Euler discretizations, and perhaps, and I haven't worked out all the details, but even Runge-Kutta discretization and other discretizations are going to be discrete time contractions. So how do you prove this? You prove that 2 implies 1. So proving that 2 implies 1 is very simple. And you just find, if you have one alpha such that this thing is true, you easily find out that the one-sided Lipschitz constant must be negative. Proving that 1 implies 2, you need to find out what values of alpha are such that this happens. And it turns out that if 1 holds, then it's not true. It's not only true that there exists an alpha. It will be true that if alpha is such that the discretization is contraction, then anywhere from 0 to alpha is also working. So another way to put it is that so long as alpha is sufficiently small in an interval, all of those discretizations are going to be contracting. All right. So here's the second half of the theorem.
So alpha is in an interval. One alpha is enough to get
one alpha is enough to get contractivity of the original vector field. But I have not studied the problem. If you give me a range of alpha, what is the optimal contraction rate of F? I have not worried about that. I have worried of the other problem. I've worried of the problem. If I know, let me tell you this problem, and I have not worried at I have not worked at the converse because I didn't know it was important. Suppose I tell you that you know what the contraction rate is. It is called, let's call it C. Suppose you know C, and now you ask yourself the question, for what ranges of alpha is this contracting? And can you get me an optimal value of alpha? And I put a star over optimal because I'll come back to that in a second. All right, so I can do this for you. It's a little bit of a long story, but first off, the very natural thing to do is I cannot do it only as a function of C. I need to take a Lipschitz constant of F, let's call it lowercase l, and I'm going to define the ratio between L and C. And it turns out that the Lipschitz constant compared with the one-sided Lipschitz constant, it's always larger. If you just look at the formulas and you use Cauchy-Schwarz, you can see that the Lipschitz constant is always larger or equal to the one-sided Lipschitz constants. Therefore, when I do the ratio between L and C, it's always greater than or equal to 1. And it really makes sense to call that the condition number of the nonlinear map. So the condition number of the nonlinear map is the ratio between the Lipschitz constant and the one-sided Lipschitz constant. It's always greater than or equal to 1. Okay, so now, what do I have? I have the following statements. I have that independently of the norm, for any norm that you may choose, this is a range of alpha that works. So any forward Euler discretization in that for those values of alpha will be a contraction. And the Lipschitz constant of that map will be upper bounded by this particular, I cannot say it's again, it's one of those things that only I can love. But anyway, there's a formula, and that formula is guaranteed to be less than 1. So my Lipschitz constant of the forward Euler discretization, the Lipschitz constant, is strictly less than 1. So it's a contraction, right? Less than 1 Lipschitz constant. Why is it less than 1? Why? Because I can show that this term is larger than that, and I have 1 plus something positive. The inverse of that is less than 1. Now, I am making no assumptions on the norm. If I knew that I had a 2 norm, or I knew that it was the infinity norm, or a weighted infinity norm with positive diagonal weights, or I could get better bounds. So here, this range is for any norm, this range works. It's not the optimal range for your particular norm that you may find in your example, but this is guaranteed to work. And now I can do the optimal step size, but optimal here does not mean you run the code and you're guaranteed this is the optimal range. No, I'm now going to minimize my upper bound. And therefore it's optimal with respect to the upper bound. But if I knew that it's an infinity norm, I can get a better upper bound and I can optimize that and I get much better than now, right? So it's optimal, but I put a star around it there to just remind myself not to mislead anybody. And anyway, so you can do that. And the optimal step size here, it's a little difficult to get it in closed form, but in any case, here is a Maclaurin expansion for that, and the same is true for the resulting contraction factor, less than 1. At the end of the slide deck, there are the 2 norm and infinity norm cases worked out, very similar to this, with different ranges of alpha, values for the Lipschitz constant, optimal value of alpha, optimal value of the Lipschitz constant. Does that make sense? And you get different formulas. Any questions? All right. Next property. The next property is almost like the fundamental property of contracting systems, and that is incremental input to state stability. And the first time I read it, I was like, why would I care about this property? It's a weird name for it. It's long and boring. I wanted something simpler. So now, in reality, it's incredibly useful property. We have seen that when there is no time-varying signal, exogenous signal, we've seen that the distance between any 2 trajectories is decaying according to this differential inequality, right? and which means using the normal comparison lemma that your distance between two trajectories is exponentially fast decreasing. And by the way, one can also then use this to prove Lyapunov functions, right? Because you substitute x2 and you put an equilibrium point. First of all, you use what I had a second ago to prove that an equilibrium point exists. And if you plug it in, this is showing the distance from any trajectory to the equilibrium point is exponentially decaying. So you see, it's more powerful to have conditions on the distance between two trajectories rather than having conditions only about the distance to the equilibrium. It's much more powerful to have incremental properties rather than to have properties with respect to a fixed point. Because otherwise, first of all, you need to assume the fixed point exists. You have to already have calculated it. And then in any case, it doesn't tell you as much information as the incremental condition does. Now, I want to change or generalize this equation x star, actually not with the fixed point. I want to generalize it when I had an arbitrary second trajectory, right? I want to generalize x star to the case in which I have an exogenous signal, something that comes from the outside, a controlling, a disturbance, a set point, something that comes from the outside. And I think sometimes I call this u, sometimes I call this theta, I think of it as a parameter, I call it d because it's a disturbance, it doesn't matter, something that comes from the outside, right? What happens to equation star, right? What happens to the evolution of the distance between any two trajectories? How do I generalize that? Okay, so now the first step is that I need to continue to talk about contractivity, but now when I compute the Jacobian of f with respect to x, it will also depend upon, by the way, now also using time, it will depend upon time, and it will depend upon u. So now I have a Jacobian depends upon x, t, and u, and I want to define contractivity for this new case. So what happens is this, that whenever I say contractivity, I mean to say that the conditions for contractivity that you know have to be satisfied uniformly in the other variables. So what is this condition here? In the supremum over x of the log norm of the Jacobian of f with respect to x, maybe I'll write d sub x, to mean to say the Jacobian with respect to x at t, x, and u is less than equal than minus c for all t and u, uniformly in t and u. Does that make sense? Well, this is the differential version. I could have written the integral condition, the differential version saying that the one-sided Lipschitz constant is less than or equal to c. But now this condition, even if I take the supremum over x, sorry, I wrote my soup. It looks like it's a delta. Forgive me. I just meant to say soup. So now this depends upon t and u, right? Because in general, f depends upon t and u, so they are also in there. So what do I mean when I say you're contracting with respect to x with rate c? I mean to say that the condition is satisfied for all t and u. Instead of writing this formula, I'm going to say uniformly in t and u. In fact, I'm not even going to say it anymore. I'm just going to assume it without worrying too much about what I mean. Uniformly. And you can study the case where this does not hold, and there are generalized versions of this and bounds and so on and so forth. So I want my map f, right? I want my map f to be uniformly contracting with respect to x, and I need one more assumption. I need to know how does the signal u hit f. How does that happen? And I need to require that u appears in f in a Lipschitz way, uniformly in t and x. So basically, you look at the vectors and you ask contractivity with respect to x, uniformly in t and u, and Lipschitzness with respect to u. So u has to hit the system in a Lipschitz way. All right. Now, if I take two trajectories, what are two trajectories going to look like? One trajectory is going to have initial condition number 1. Another trajectory is going to have initial condition number 2. Trajectory 1 is going to be subject to input U1. Trajectory 2 is going to be subject to input U2. And now I want to know how does the difference between them evolve with time. All right. And the theorem says that, yeah, instead of calling it x1, x2 here, I'm calling it x and y, doesn't matter, right? I have a trajectory x of t with input u sub x, and a trajectory y of t with input u sub y. And then I didn't write it out, but the two initial conditions are not equal. I don't need that. And it turns out that the differential inequality that we have seen many times so far gets amended. There's one more term, and that term is just additive. It's the sum, well, plus the Lipschitz constant, lowercase l, and then the norm of the distance between ux and uy. Does that make sense? Any questions? There is something that I did not define, so you may want to complain to me about that. Yeah, let's talk about U for a second. So let's come back to the problem setup. So I am studying a differential equation with an exogenous signal U. U does not need to live in the same vector space as X. I mean, maybe it does, but probably it does not. And here, to emphasize this aspect, I wrote that X at time 0 is, well, X lives in capital X and U lives in capital U. They're different vector spaces. So now, what does it mean when I write that the Lipschitz constant of F with respect to U is L? Well, there is a very natural way to make sense of that. You're going to say that F of X, let me drop the time argument, it doesn't play any role, minus F X V, where both U and V belong in the input set. This is upper bounded by L, which multiplies U minus V, right? That's what it means to be Lipschitz in U, uniformly in X. Doesn't matter what X is. For all X's, there exists a unique Lipschitz constant lowercase l, such that this bound holds. Does that make sense? But the vector spaces are different. So the norms are not the same norm, huh? Just to be clear. So this is a norm on U, on the input space. And this is a norm on X, because F takes value in X. Does that make sense? So I have two different vector spaces, two different norms. And when I talk about the Lipschitz constant here, is going from one vector space with one norm to another one. And in chapter 2 of the book, there's a nice little exercise where there are all sorts of formulas describing how to calculate induced norms of matrices going from one space to another space, from one norm, the one norm to the two norm, the infinity norm to the two norm, whatever it is. So there's you do not have the same norm. There are two norms at play. And so when you look at this formula, the one symbol that I had not defined was this quantity here. This is the norm of the difference in the inputs as measured according to the norm in the input space. Okay. Now, if you look at this picture here, which was it's the old picture, but I just made sure that the blue trajectory does not land on top of the black one. Because if I have inputs that continue to persist being different from one another, of course, the two trajectories are not coming together. They're not coming together because these are different in general. But the initial conditions are going to play no role. The initial conditions are going to be forgotten because here you have still this exponential decay, right? So how can I make this accurate? Well, I'm going to use again the Gronwall comparison lemma. And the Gronwall comparison lemma, you can get even more general expression than this, but can you guys read in the back? I'm finding it difficult to raise this. It wants to go down. So what is happening here is that integrate the differential inequality at the top. And what I get is that the error, the left-hand side is the error, which is the distance between the two trajectories x and y at time t, is upper bounded by e to the minus ct times the initial error. And that's because the Gromov lemma, we saw it yesterday for essentially a first order differential inequality like that. You've got the decay. So again, the Gromov lemma tells you that the upper bound here is the solution to this with the equality sign, right? So, and that's very easy. The linear ordinary differential equation of first order. You should be able to write down the solution in closed form immediately. All right, so this is the term due, oops. This is the term due to the initial condition, and it is exponentially decaying, right? So the effect of different initial conditions is forgotten very quickly. People say that contracting systems have the memory for forgetting property. And then, literally, what I should have in here is, because I'm trying to keep it high, is an integral of the convolution between the error, the impulse response, and the error. So here I have upper bounded the effect of ux minus ui and said, let's just worry about the supremum value that you obtain for ux minus ui. And what left over you can integrate, you can express out explicitly. And it is of the form L over C, which multiplies e to the minus CCT. So just so that we all remember, if I wanted to plot 1 minus e to the minus CT as a function of time, this would start at 0 when t is 0, 1 minus e to the 0 is 0, and then it asymptotes very quickly at 1, right? So here, this term in the parentheses, let's pick a different color. This term here, I am plotting it there, and it goes to 1 very quickly, right? So if I were to just look at 3-4 times the time constant 1 over c, it would be essentially L over c times, so the fundamentally it's L over c times the largest value taken by the difference in it. And this is the proof. And with the pairing properties, it's really elementary. You could almost just read it for yourself. You may be bored by now. I have 2 trajectories. I multiply the norm into the time derivative. I use the curve norm derivative formula, and I get the x dot, y dot. I plug in f of x, f of y, because x dot is equal to f of x, and y dot is equal to f of y, comma ux, comma uy, into x. Then, oh, there is a trick. It's good that I did this. Now you apply a trick. Now you apply a trick. I want to teach you this trick. You should know it. It's very simple. And it's always good to know new tricks when you do the proofs. So you are comparing 2 maps, and they have 3 arguments, but the first argument is the same in both. So that is not going to play it. That's not going to give you any problem. But now you have x ux, y uy, and you would like to get Lipschitz constants out of this. And you cannot have, when you have a Lipschitz constant, you can only change one thing at a time. You want to change one thing at a time, but you're now changing 2 things. So now the trick is to sum and subtract 0. What is the trick? You have f, pardon me. You have f of, let me drop the time argument, x ux minus f of y uy. So you sum and subtract the same quantity, which will be a mixed quantity. It would be f of y ux. You sum it, and then you subtract it. F of y ux. So if I sum and subtract the same quantity, I haven't done anything, right? And then you rearrange it. I should have done it better to begin with. I should have done it better to begin with. You subtract this from that, and this from this. And now what have you achieved? Well, not all that much, but now it's only ux is the same, right? You have a difference between x and y. So this is going to have to do with the one-sided Lipschitz constant, because we're looking at x and y. And here instead y is constant, so it's the second argument, and that's going to be looking at the at ux minus uy, right? Sorry, I didn't write this very elegantly, but the point is that here you have x ux, y uy, and in the next row you have x ux, y ux, y ux, y uy. And now the only thing you can ask is this: why were you able to just split this up? There are two terms. I sum and subtract two terms, so I get four terms, and then I do less than equal and I split it. What is the property that allows you to do that? Well, it's written on the right, and the property is subadditivity, because the pairing is subadditive in the first argument. See, it's magically how it actually just works. Now, the first term is exactly the definition of one-sided Lipschitz constant. It's exactly fx minus fy into x minus y. Uniforming ux doesn't matter. It's upper bounded by minus c x minus y squared. This is the definition of one-sided Lipschitz constant, the integral definition, not the one with the Jacobian. And then what am I left over? The second term. The second term has y is the same, and then I change u. But now, if you change u, oh, sorry, I am doing it slowly. I didn't do anything. So right now, I take this and I copy it. Okay, so this I haven't applied anything yet. So now the question is, how do I work with this? You know, I want to get out the Lipschitz constant of the first term. And so for the first time, I'm going to use another property of pairing, which is the Cauchy-Schwarz inequality, which was one of the four properties. So the norm of, no, not even the norm. Well, the absolute value of the pairing x, y is upper bounded by the norm of x times the norm of y. This is Cauchy-Schwarz, and it applies to the weak pairing as well. It was one of the axioms that I mentioned. And so what you get here is you get that instead of having a pairing between those two things, you have the norm of the first times the norms of the second. And now the norm of the first is exactly the assumption of Lipschitz with respect to the input, uniform in x and t. Therefore, the final row is the one that comes to be. Finally, I have obtained that minus c norm squared plus L norm difference in u, norm of x. Bless you. Now, and then the final step is always the same in this proof. You eliminate out the one copy of the norm. So there's norm of x minus y here. There's a square there and a copy of x minus y here. So you eliminate from here, from there, and from there, and you get the formula that I had in the previous page. Does that make sense? You get this formula here. Fantastic. All right, very simple. I will skip this slide. It has to do with the fact that if you can define the norm of a signal, you use that signal as an input into a contracting system, and you compute the norm of the signal of the states as a signal norm. So now you're integrating over time. And you can prove that contracting systems have an integral system gain equal to L over C. So if you find this interesting or you ever need it, this is in the book with the little proof. All right. Next property. Next property. Have we taken a break today or not yet? We haven't taken a break. Let us take a 5-minute break. All right, welcome back. So, at this point, I would like to show you a little application, if I may, of the incremental ISS property of this ordinary differential inequality with respect to the Dini derivative of the error. I think of this as the error. It may not be the error in some cases. Maybe it's a desirable quantity, but in any case, instead of having to say the norm of the distance, the norm of the difference between x of t and y of t, I just call it the error. Now, one more warning about nomenclature. So in this equation, L is the Lipschitz constant with respect to the input. Other times I'm gonna half an hour back I used the L. I realize I apologize. Also for the Lipschitz constant of the vector with respect to the state when I was computing the Euler forward Euler discretization. But I just realized that this is the Lipschitz constant with respect to the input. Okay, fine. I'll make change notation later. All right. So I'll make the two usual assumptions. contractivity, one-sided Lipschitz constant with respect to x, negative OSL, and contractivity with respect to u. Well, then, at each fixed u, when u is fixed, the system is contracting. Well, then I must have a unique equilibrium point, right? But the equilibrium point depends upon u. It is not invariant of u. You change the parameter, the equilibrium changes. You change the parameter another little bit, the equilibrium changes another bit. So the equilibrium is not a point. The equilibrium is a map from the input, from the parameter, from the disturbance to the state. What is the map? So it's a map, right? It's from u into x star of u. So what can you say about the properties of this map x star of u? Any? Okay, so this course is about contractivity, but I told you contractivity is negative one-sided Lipschitz constant, and here we're making a bunch of Lipschitz assumptions. The consequences of a bunch of Lipschitz assumption, you know what it is usually? A Lipschitz property. So that would be quite natural if you were to have it. And the property is that, yes, the equilibrium map is a map from the set of inputs to the state. And this map is Lipschitz. And the constant is no more than L over C, which we have been playing with for the last 20 minutes, half an hour. Does that make sense? L over C. So this is an immediate consequence. Well, yeah, I have the proof. It's an immediate consequence. If you take the formula that we have written many times, you plug in a constant input for the first U1 and so the two inputs are time independent, so they're just constant. Then, as you let the first trajectory go, it will converge to the first fixed point. If you let the second trajectory go on its own, it will converge to the second fixed point. Well, then take the formula that we have and take the limit as time goes to infinity on left and right-hand side. The left is going to go to 0 because as you stop at your equilibrium point, you're not moving anymore, and the time derivative of the distance is going to be 0. And then you have that, then you get a formula. The two fixed points are going to go to the limits, and the two inputs are constant, so they don't change. And now from there, you immediately get what you need immediately. So it's an immediate application. So before I leave this topic and I talk about the next property, let me just talk about convex optimization. Here's a sensitivity result, which I have not seen anywhere, but that's because I'm not very familiar with all of the literature on. But in any case, still, it's interesting to notice that what this is implying is that when you have a strongly convex function, which is differential with respect to the state x, and its Jacobian, its gradient is Lipschitz with respect to u, then the global optimum of your convex optimization problem is a Lipschitz function of the parameter. All right. Let's keep that in mind for later. Okay. So I have a lengthy property and then easier property. So let me tackle head on the last complicated topic for today, and then we'll have little comments, and then we'll wrap up. So it works like this. It has to do, yesterday I gave you this intuition that sometimes you can define a norm on a big space by defining norms on each of the subspaces. And then after you get all of these non-negative numbers, you combine them together with yet another norm. Maybe you sum them, or you take the square root of the square, or you take the maximum of them. That's basically another norm, right? So you have n local norms for each of the subspaces. Then you have an aggregating norm, and altogether you obtain a composite norm. I know the language is heavy because there are 3 words to remember instead of, you would like it to be 2, but it's actually 3. Because you have the local little norms, and then you aggregate them. So imagine that you have, what is the notation I use here? Sometimes I change notation, it's terrible. So imagine you have n lowercase subsystems. Each subsystem has dimension capital Ni. And so then when you sum them together, n1 plus n2 plus n sub n, you get capital N. All right, fine. So now you have lowercase n norms for each of the subsystems. So right here I have a picture of what is it, 8 subsystems. They don't need to be the same dimension, and these vector spaces don't need to have the same norm. It doesn't matter. So that's why I color them with different colors. And these systems are interconnected. That's why I drew the edges between them. And if you were to compute the Jacobian, and what does the interconnection mean? It means that the evolution of the state of this system depends upon itself and the values of the state of the other systems. But if there is no edge, then you're independent of that, right? Not directly. So if I compute the Jacobian, and trust me, it's much easier to read on my computer. If you compute the Jacobian, it will have a certain structure, right? This is the topology of the interconnection. All right, fine. Yeah. So on R capital N, where capital N is equal to N1 plus capital N lowercase n. Does that make sense? So I have lowercase n subsystems. Each subsystem has its own dimension. I define a norm, a local norm on each subsystem. Then I define an aggregating norm that tells me how do I sum the norms of the error at each state to get a norm on the full system. Together, the local and the aggregating norms define the composite norm. Now, the question is obvious. The question that I want to answer is obvious. When is it true that if I have lowercase n independent subsystems, each of which I'm going to assume is contracting, because what else am I going to do? When is it true that the interconnection of contracting subsystems is contracting? That's a very basic question, right? So the contractivity of the subsystems is going to be respect to the local norms, and the contractivity of the full system is going to be with respect to the composite norm. This is the objective. And now I'm going to I already made an assumption. Each subsystem is contracting. What is the other assumption that I am going to make? I already mentioned to you that if you look at this picture, here, this system, the evolution of that dynamics is depending upon these edges, right? So if this is x3 and this is x4, then x3 dot is going to be equal, I don't know, f3, which will depend upon x3, but it will also depend upon x4, right? And other variables. I don't know, x5, x6, actually precisely x6, not because there's no edge there, right? x6. So what am I going to assume about the vector field f3 that describes the evolution of node 3? How does that depend upon the state of 4? Well, there's a natural answer to that question. Anybody willing to throw it at me? Lipschitz, because it's a course on contraction theory, which has to do with Lipschitz properties. So I'm going to assume Lipschitz with respect to 4, and once negative one-sided Lipschitz, which is contractivity with respect to 3, right? All right. Let's see okay. So I am going to adopt this notation from game theory. I suppose you have already seen it. It works like this. The evolution of the state of node I depends upon its own, local vector field, which is a function of the state of node I, and that's fine. And then it depends upon some of the other states. So it's just good to have a notation for the other states, which are not I. And I could write x1, comma, x2, comma, dot, 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 xi minus 1. And then I should say xi plus 1, xi plus 2, all the way to xn. Instead of this nightmare of notation, allow me to use this weird symbol, which is minus I. So whenever I write x minus I, this is in game theory very widely used. It just basically says all of the other states that are not I. Okay, so just, all right, perfect. Perfect. So I'm going to make these two assumptions. I'm going to make the assumption that the vector field fi has negative one-sided Lipschitz with respect to xi, which means that it is contracting with respect to xi. And do I need to say that I mean to say this is uniformly in x minus I? And then I will assume that fi with respect to xj is Lipschitz, as a Lipschitz constant. And I mean to say uniformly in x minus j. So for all of the variables that are not xj, it's uniform. And if you look at both formulas one more time, you basically have a collection of contraction rates, C1 C lowercase n. And then you have all of these Lij's for I different from J. Does that make sense? These numbers are all positive, right? The C's are positive and the Lij's are positive. Now, when people give you Lij for all I and J except I equal to J, then these coefficients are screaming to be placed inside the matrix. Where you're going to write, let's say we do the case with 3. So you're going to put L12, L13, L21, L31, L32, L23. And now this matrix doesn't have something on the diagonal. What are you going to put on the diagonal? Well, how about we put the contraction rates? Maybe we put them with a negative sign. We call this the gain matrix. And instead of G, because it's a graph, let's use the Greek symbol for it. Let's use a capital gamma. So I'm going to, given that I have made these assumptions, it's very natural to define the associated gain matrix where you stick in all of your Lipschitz constants. And well, these are minus because they were negative to begin with, really, right? Okay. So now, what does this gain matrix gamma? What does it look like? What properties does it have? This matrix gamma is one of those matrices that lives in that magical set that I was joking about yesterday, which is to say it is a Metzler matrix. All of the off-diagonal entries are positive or zero. Well, they're zero if there is no dependency, right, between the nodes. Otherwise, they're positive. So it's Metzler, and Metzler matrices have magical properties. There's a theorem for them, for example. So either the gain matrix is Hurwitz stable or it is not. And we can quickly check. Why don't we check? Why don't we do a simple calculation, just you and I right now, for a simple case. My goodness. All right, let's go like this. So suppose I have a matrix minus C1, L12, L21 minus C2. Where can the eigenvalues be? Okay. And let's call this gamma. Well, then it's clear that the trace of gamma is equal to minus C1 minus C2, which is negative, which is the sum of the two eigenvalues is negative. So now, the two eigenvalues have a negative sum. If the determinant is positive, both eigenvalues are negative, and the sum of two negative numbers is negative. But if the determinant is negative, one of the eigenvalues is negative and the other is positive, and they sum to something negative, but one eigenvalue is positive, which means the matrix is not Hurwitz. So really, I need to look at the determinant. And what is the determinant going to be? The determinant is going to be C1 times C2 minus L12, L21. And what do I want? I want to have both eigenvalues negative because I want my system, my matrix, my gain matrix to be Hurwitz. I want the eigenvalues to be both negative, and their product, which is the determinant, has to be positive, right? So the statement is gamma is Hurwitz if and only if C1 times C2 is greater than L12, L21. So this is a small gain theorem. It is saying that the contraction rates at the two nodes need to be sufficiently large, larger than the product of the Lipschitz constants. If you want to make it look even more like a small gain theorem, you can think about a situation where you have a node which satisfies x1 dot equal to minus C1 x1 plus L12 x2, and you can rewrite this condition as C1 over L12 times C2 over L21 greater than 1. And this really exactly is a state gain, an input gain from node 2 to node 1. So, okay, so I didn't write the full theorem. So let's look at the full theorem. The full theorem says this. Make the two very natural assumptions of contractivity of each node and Lipschitz dependency among nodes, right, across edges. Construct the canonical gain matrix. It's unavoidable. It's Metzler. And Metzler matrices, it's either, it could easily be, it doesn't need to be Hurwitz. I mean, I can give you easy example, right? I mean, here, if I set -1, -1, 10, 10, I can assure you the eigenvalues of this matrix have one of them as positive real part, for sure. If the matrix is Hurwitz, if it's Hurwitz, then the interconnected system is strongly infinitesimally contracting. I didn't tell you the rate, and I didn't tell you the norm, but all you need to check is that the matrix is Hurwitz, and checking the Hurwitzness of a Metzler matrix is akin to checking a small gain theorem. The contraction rates have to be larger in some sense than the strength of all of the interconnections. Now, here, all of the interconnections are treated in an adversarial way. They're like worst case scenario. If I have an interconnection, suppose I have a neural network and an edge plays the role of an inhibitory signal. So node J is inhibiting node I with a certain strength. No. Here I am upper bounding the strength as if it was exciting node I. So this is a conservative condition for contractivity. It's assuming that each dependency is bad. Also because, for the record, to be clear, the spectral abscissa of the Metzler matrix will increase if you increase any entry of the matrix. If anywhere you add a positive number, the spectral abscissas will only either remain constant or move to the right. So if you diminish the contraction rate, or if you strengthen any one of the edges, you're moving to the right. So all of the edge weights are playing against you. So it's a sufficient condition, but it's very elegant. It's very clean. You should really know it because. So if you have the question, oh, I have a contracting system and I have another contracting system, is an interconnect them? Is it true the interconnection is contracting? The answer is, well, yes, it is. If the gain matrix is Hurwitz, but not always. Not true that it is always contracting. And then if the gain matrix is not Hurwitz, you don't know. Now you need to roll up your sleeves and work harder to find out what is the proper composite norm on the full space with respect to which you are contracting. Question.
Why this is sufficient and not necessary?
Because here you see I am using ultimately I am using this equation, right? This ISS bound at the heart of the matter, and so U2 here, this is the effect of the states of the other nodes, and U2 it's treated as if it was always excitatory as a signal. It's always just increasing. Imagine that I have an energy at a node like a Lyapunov function, and then there arrives a signal. I'm always upper bounding the increase in the Lyapunov function as a function of the Lipschitz constant. But instead, maybe that signal could be inhibitory. I mean, another way to yeah, is that another example? Maybe this example will work. Imagine I have linear systems. X1 dot is equal to minus X1 plus 10x2. X2 dot equal to minus 10x2. Oops, I meant to say minus x2. So the matrix here now is -1, 10, minus 10. Is this matrix Hurwitz? Is it Hurwitz, yes or no? You can eyeball it. Why? Why? Alpha of A, the spectral abscissa of the matrix, is always upper bounded by mu2 of A, which is the log 2 norm of A, which is equal to lambda max of A plus A transpose over 2. A over A transpose over 2 is equal to -1, 0, 0, -1. Isn't it? Because I did it on purpose, because +10, -10 simplify. when you take A plus A transpose, the skew symmetric part goes away. And now lambda max of -1 is -1. So this matrix is Hurwitz, right? Yes, this matrix is Hurwitz. But if I use this approach to proving contractivity, how did I treat the signal from node? I apologize, there's a typo here, forgive me. Of course, I meant to say x1 here, right? Otherwise, I don't have that matrix. In the contractivity theorem, I have tried to upper bound the effect of node 1 and node 2. And I said, what is the Lipschitz constant of node 1 on the vector field for node 2? And that value is +10, right? That Lipschitz constant is +10. So what I have done is tantamount to working not with A, but I have asked for the Metzler majorant of A to be Hurwitz. Now, it is true that if the Metzler majorant of A is Hurwitz, this does imply that A is Hurwitz, but the converse is not true. The converse is not true. Because the bounds that I showed you yesterday say that alpha of A is upper bounded by alpha of the Metzler majorant of A, and in fact, it's upper bounded by alpha of the Metzler majorant of A plus any non-negative matrix B, right? So this could be Hurwitz, like in the example with the +10 -10. But then this now, after I lose the information about the plus-minus sign of the off-diagonal entries, this is not Hurwitz anymore. Yeah, because 110 plus 10, 1 is for sure negative determinant, which means that one eigenvalue is positive, one eigenvalue is negative.
The matrix that you were showing, the major and
Yeah, if I were to start with the linear system and I were to apply this, I would get that this A matrix is the Metzler majorant of the matrix that I started with, of the matrix A. And when I do this process, I lose information about the signs of the interactions, which a scientist like you would hate because you're interested in science, right? So, but as I said, it's a conservative approach, but it's an approach nonetheless. Oh, I need to have a way. If you only give me nodes of each of the states, I don't know how to aggregate them. What is the optimal norm to use here? What is the aggregating norm on the? Oh, by the way, let me just clarify one thing. This is lowercase m, so there are n lowercase m subsystems. So this gain matrix is not the dimension of the full system, right? It's a dimension only. So I have obtained the gain matrix on the number of subsystems, not on the dimension of the whole system, right? I've already reduced. So now the question is, what is the optimal? Can I? The question is that these theorems speak for n aggregation. No. This theorem, I didn't spell it out fully right, but this theorem is to be understood as there exists an aggregating norm with respect to which the interconnected system is infinitesimally contracting with a certain contraction rate.
What is the theorem for which second round of
Yes. No, I haven't chosen it yet. Yes. So the theorem goes like this. Well, let me just edit the slide. So let me see. Sometimes you simplify the presentation and okay. So I am given my network systems with all of the components that I have to have. Then I have to say, given local norms. Now this I does not mean the Li norm. This is I just adding the index. Then assume these two properties, right? I must introduce local norms now Because otherwise I cannot even make this statement. Like to make contractivity, I have to have a local norm. I do assumption 1, assumption 2. With assumption 1 and 2, I construct the gain matrix. And that's assumption 3. And then the statement is to be understood as there exists an aggregating norm such that the interconnected system is infinitesimally contracting with respect to not the aggregating norm, the composite norm. I don't know what is a Lyapunov function for a good equation for, that's right. Yes, yes, that is correct. I should maybe show you the magical theorem about the magical matrices so that you can see everything. Let me delay that for another minute. Let me just tell you what is the rate. So, and the rate is, the contraction rate is equal to the spectral abscissa of gamma. Well, absolute value of that. So the gain matrix is Hurwitz. It has a maximum eigenvalue that is strictly negative. That is the contraction rate. Actually, that is the contraction rate. There is a little detail with the 3 eigenvalues that are repeated. So maybe this plus epsilon in the worst case. Where does the optimal aggregating norm come from? It comes from the main theorem about Hurwitzness of Metzler matrices. It comes from there. And then alternatively, that theorem, you know what the theorem is? It's in the chapter on logarithmic norms, where I talk about designing optimal logarithmic norms for Metzler matrices. So that's the full story. I did not write the full story here because I need to end up defining a whole bunch of symbols. Yeah. Are you with me? All right. Yeah, fine. So, oh, I made a mistake. Earlier, when I said small gain, I wrote C over L greater than 1. That was a large gain. My mistake. Sorry. I meant to say L over C has to, the product of the gains, which are L over C's, those need to be less than 1. Right. By the way, the proof, I'm not going to do it, but in case you wonder, it uses the same properties that you have seen, combine them together. It's the same properties of the weak pairings, contractivity, and just a tiny bit of understanding that if you have a Metzler matrix and it's Hurwitz, then you can find the diagonal matrix positive eta such that this matrix is negative definite. And this is from the Metzler-Hurwitz theorem. All right. With this, I am going to stop, and tomorrow in lecture 5 and 6, I'll start by finishing up these properties and do applications. Thank you all, and have a great day. Enjoy.